Well, I think we laid a pretty good foundation for statistics in Chapter 5. Now we're going to look at more ways we can work with statistics as far as with the data. We can characterize the data. Excuse me, we'll look at measures of variation. We'll look at something called a normal distribution. So now we will get into a little more depth with calculations with respect to statistics. But in the media, we see statistics used in opinion polls, graphics, summaries of statistical studies, or even attempts to establish cause and effect. Now let's look at some calculations using some of the tools in this chapter that we'll use that will give us a very strong introduction to the powerful science of statistics. So let's take a look at Section 6A with Characterizing Data. Now back in Chapter 5 we saw a frequency table, and we actually saw a few graphs that could show us how the data are distributed over various categories. So more formally we can say that a frequency table or a graph gives us the distribution of a data set. We're interested in how our data is distributed, maybe with respect to grades. So how are my grades distributed? How many A's, how many B's, how many C's, how many D's, how many F's? So that would be the distribution of my data set. And we can do it with a table, that frequency table, or graphs and histograms. One very important note, and I'm going to put it right here. For all of Chapter 6, we can only work with quantitative data. Only quantitative data is going to be used here because we will be making some calculations such as averages and some standard deviations, and that can only be done with quantitative data. And remember, with quantitative data, when we had our frequency distribution, the values here in this X column were all numerical and had a specific order to them. That's what made the data quantitative. So that's the type of data we'll be working with here in Chapter 6. So we'll start off with the very first calculation we can make, which is the average. The word average takes on several meanings and can be misleading depending on which of these values you use. So it's used so often that we're going to study the three common ways of characterizing this average, or it's sometimes called the center of a data distribution. So the three common ways of calculating an average, which I'm sure you heard of, are the mean, the median, and the mode. All three of these are actually called averages. And another way for an average, or a description of an average, is we're looking for the center of a data distribution. So the mean average is the one you think of when you're like calculating your grades. When you add up all your test values, let's say you had 6 test values, and you divide by 6. So every piece of data is included, add them up, divide by the number of pieces of data. So that's the one you usually think of. The median is the exact middle value in a data set that's been sorted. So it's the halfway mark between the upper half and the lower half of your data. And if you happen to have an even number of values in your data set, then you take the two middle values, you add them up and divide by 2. And so you kind of take the mean average of the two data values that are in the middle when you have an even set of data. An example will help clear up any misunderstandings there. And finally, the mode, it's that value that's most common in a data set or a distribution. So let's just put those guys to work. So here's an example, and I have a data set that represents body temperatures of randomly selected individuals. So it appears I have 11 pieces of data. So if I want to calculate the mean average, then what I'm going to do is I'm going to add up all those pieces of data, and I'm just going to divide by 11 because there are 11 pieces of data. So take a second and add those up. So if we add all those temperatures together, we should get 1086.30. If we divide it by 11, we get a mean average temperature of 98.75. Okay, so there's our first one. Okay, second one, we want to find the median. And if we go back to the statement of the definition, the median is the middle value in a set of data that's been ordered or sorted or ranked. So what we have to do with the data set is, I can't immediately come in and find that middle piece of data until all that data is sorted and ranked. So let's go from smallest to largest. So go ahead and rank that data. Now that the data is ranked from smallest to largest, we can actually go in and find that middle piece of data. So it's just you count in 1, 2, 3, 4, 5. So we find one right smack dab in the middle, 98.4. So that value is our median. Now when I ranked this data, knowing that I had 11 pieces of data, I knew that there would be 5 below it, 5 above it, so I really just needed that 6th value. So when I was ranking it, I could have stopped at 6 because I knew that that value would be my median. Now if I had an even number of pieces of data, let's say instead of 11, I would wipe out that 1039 and I only had 10 pieces of data. Well, since there wouldn't be a value that stood out directly in the middle, I'd have to take the 2 pieces of data that were in the middle, add them up, divide it by 2, and find the average of the 2 middle pieces. All right, so let's continue. The last thing we want to determine, the other average, is the mode. And the mode is that piece of data that occurs more often than any other piece of data. And it's kind of nice to look at the ranked set, and I noticed that 98.4 occurs more often than anybody else, so the mode would be 98.4. So I have 3 different averages for that data set. All right, so what if, already took care of this. If there was an even number of pieces of data, you would just rank them, and you would find the average of the 2 middle pieces, the 2 middle values. All right, so let's see what else I've got here. Let's talk about something called an outlier. When you have a data set and it's clear that there is a value that is much lower than the entire data set, or if it is much higher than the data set, then that particular piece of data is called an outlier. And an outlier can change the mean of your data set, but it will not affect the median or the mode. So we're going to look at a data set and see if there were any outliers. Actually, let's go back to the data set of body temperatures. With my ranked set of data, as I look at it, I notice that there is one value that's quite a bit higher than the other values in the data set, which I would consider that to be the 103.9. That's a bit higher than the rest of the values. So if this was from randomly selected individuals, this one I would call an outlier, and it might be because that person is sick. Now, if you throw out an outlier, then you might get a better idea of what the average temperature might be, because that outlier has a tendency to skew the mean towards it. It's kind of like a magnet. An outlier is a is like a magnet, and it pulls the mean towards it. In this case, I'm kind of showing with the median, but it's actually the mean. Think about what is the average temperature for a human, for a person. The average temperature is 98.6. Now, how did they get that value? So if it's above that, you're considered to have a temperature. Actually, my normal temperature is not 98.6. My normal temperature is actually less than that. Some people's normal temperature might be above that. But this is just an average. If you take a whole bunch of people and find their temperatures, the average would be 98.6. Okay, so let's go back. So that outlier will have a tendency to skew the mean of a data set. So let's look at this situation. We've got a track coach that wants to determine an appropriate heart rate for her athletes during their workouts. So she reads the following heart rates as these athletes are working off of a heart monitor for 5 of her best runners. And so the values she determines, or she obtains for these athletes, are 130, 135, 140, 145, and 325. Whoa, you may look at that and say, wow, that number seems a bit off. Well, we'll categorize that as an outlier. We'll see what it does. But for now, let's take those 5 pieces of data and calculate the mean and the mode. So you do that. I misspoke a second ago. I said we want to find the mean and the mode, but I meant the mean and the median. So I come up with a mean of 175 as a heart rate and a median as 140 for a heart rate. Let me check my values there just to make sure. Give me a second. So I double checked my values. So we have 2 distinct values, the mean and the median. Well, they differ from each other by about 35 with respect to these heart rates. So answering a couple of questions with that. Does there appear to be any outliers? Yeah. That 325 is way out there. It could be, when you get an outlier, it could be that maybe the particular heart monitor that was on that particular runner was malfunctioning and it gave a wrong result. Or the person recording these heart rates could have wrote a number wrong or interpreted a number wrong. So we've got to be careful, and those things, those outliers can really skew your results. So what we want to do is throw the outlier out. So let's throw out 325 and recalculate the mean and the median. So do that, throw out 325, let's find the mean, and let's find the median. So if we throw out the 325 and find the value of the mean and the median, the mean would be 137.5 if I add them all up and divide by 4. And the median, since I now have 4 data values instead of 5, the median is 137.5 because I have to add the 2 pieces of data in the middle together and divide by 2. Notice that these 2 numbers give us a much more accurate picture of the average heart rate for those athletes than would 175. So, the moral of the story is, when you have outliers in your data set, then your median is the better value to use for an average when there is an outlier. So that answers this question. Which value would be the better average to use for this data set? Any data set that has an outlier, you want to use the median value as your average as opposed to the mean. Because over here, the median is a much closer, much more accurate picture of the heart rates of those athletes than the 175. So we'll use the median. When outliers are present. So we're not going to take the time to throw out the outlier and recalculate the data. We're just going to make our calculations, mean and median, and if we notice there's an outlier, we're going to just say take the average as the median. Here's another situation. Suppose I surveyed every one of you and asked you for your yearly income. And we calculated the mean and the median and the mode, but Bill Gates walks into the room. How would his yearly income affect those previous values that we found? So his salary would certainly change some of those values. Definitely the mean, because the mean takes into account every piece of data. So suppose the mean was, I'm just putting a number up here, 26,000. When he comes in, I have to take his salary, and let's assume it's this exorbitant amount of, $100 million a year. When I put his value, his data value, in with the other sets of data, it's going to have a tendency to draw the mean towards that value, and this mean is not going to be a good representation. Is that 100 million? Yeah. I think so. So when you have an outlier such as that, you don't want to use the mean, because that outlier, again, is like a magnet. It's going to take that 26,000 and pull it towards it, where it will no longer be a representation of the regular population. Just another case where the median is going to be the better value to use, because it's right there in the middle and it does not get pulled towards that outlier. So in this case, again, we just give another example for the case where the median is the better value to use when we have outliers. Okay, I will pick up with this on a next video. So I'm going to stop this one right here.